late, but we have one more talk, and it's only 10 minutes, so we'll be shortly on our way to lunch. You, Jeremy, are the only person standing between us and lunch.
Yeah. So sorry, it's a tough place to be the only one standing between you and lunch, but excited to tell you about human computable passwords. This is joint work with Manuel Blum, Anupam Datta, and Santosh Vempala. So since this is before lunch, I thought I would start off by giving you some philosophical questions to think about. The first philosophical question is privacy dead? And the second question is, what types of functions can a human compute in his or her head without any assistance? What types of functions could we compute quickly in our head without any assistance? So I don't have complete answers to either of these questions. If you do, please come tell me. But I do have an interesting problem to think about these questions. So consider the problem of password management. This is the problem we all face every day when we go online, and you have to create passwords to authenticate yourselves to different services that you use. Now, typically, you have two competing goals when you create your passwords, security and usability. Security means you don't want the attacker cracking into any of your accounts, and if there's a breach at one of these accounts, hopefully you want to make sure that the attacker doesn't crack into any of your other accounts. Of course, usability means that you don't want to tear your hair out trying to remember all of these passwords. And this is a difficult question for most humans. So why do I think that this is a good problem to look at to explore the two questions? Well, fundamentally, it's asking a question about human capabilities. What are we capable of doing? And also, fundamentally, I'd argue that if authentication is an unsolvable problem, then probably we do live in a world where privacy is dead. I don't believe that that's true. I think that authentication is possible. But I think that this is a central question to the debate. OK, so of course, remembering passwords is hard. So one coping mechanism that people might adopt is to kind of offload all this work to software, password managers like LastPass or 1Password or Password Hash or whatever other program you might use. Of course, now you're really trusting your computer, right? So you have your laptop. Maybe you log in with your cell phone. Maybe you authenticate from public computers at the library. Maybe your office computer. Maybe occasionally you'll use friends' laptops. What happens if one of these devices is infected with malware at one point in time when you enter your master password? In this case, all of your passwords are compromised. Or even more simply, maybe instead of malware-infected computers, maybe just someone looks over your shoulder while you type in your master password. I doubt many of you wear one of these sweaters when you authenticate. All right, so the question that we look at is it possible to obtain stronger security? There's lots of scary news stories, RSA secure ID tokens that are compromised, growth in password leakage, keyloggers are skyrocketing, more stories about keyloggers. Heartbleed, of course, could result in the leakage of any password that you typed in. And finally, there's several separate instances of security vulnerabilities in LastPass. So if you use LastPass with one master password, there's a good chance that an attacker was able to brute force the master password if you haven't changed it since this incident. And this is a separate instance, so LastPass seems to be a real whipping boy for hackers. All right, so our scheme is really looking at the question of, is it possible to perform authentication without computer assistance? In particular, we want a human computable password scheme where passwords are computed by responding to public challenges. And I want to stress that all these computations should be done in your head, not on hardware, entirely in your brain. And we'd like to develop a scheme that remains secure after many breaches. So, if an attacker cracks into LastPass, or Sony or some other organization, hopefully you shouldn't be able to obtain all of your other passwords. And in fact, even if you looks at many of your passwords, we're hoping that all of your other passwords remain secure. And finally, there's a usability constraint here. We don't want to introduce something that's too complex for a human to execute. This means that really whatever protocol we propose needs to be limited to simple operations. So for example, addition modulo 10, if I give you the numbers 7 and 6 and ask you to add them, you could probably do it. However, if I gave you these two numbers and asked you to add them in your head, my guess is most of you would just give up fairly quickly. So we have pretty severe restraints on the types of computation that we can do in our brain. One of these constraints is that operations that we perform in our brain have to be carried out in very limited memory. So we have 7 plus or minus 2 chunks of information that we can keep in our brain. So essentially, any algorithm that we execute in our brain has to be a streaming algorithm that uses space at most, let's say, 5. All right, so with these constraints, how do we design a human authentication scheme? Well, our protocol starts by asking the human to memorize a random mapping from images to digits. And this is the hardest part of learning the scheme. I memorized such a random mapping, actually from 100 images to digits. It took me about 2.5 hours. So I would conjecture that if you're motivated and you wanted to teach yourself a random mapping, you could do the same in about 2.5 hours. It is a big time commitment. So right now, that's one of the open questions: is can we reduce the pre-computation aspect of the protocol? But OK, let's suppose that you've memorized a random mapping from images to digits. So lightning bolt goes to 9, dog goes to 3, et cetera. Now, how do we? OK. Oh. Yeah, you can use mnemonics to hopefully make this task easier. I didn't have mnemonics when I memorized my mapping, but if you did, it might be a little bit easier. OK. Anyway, let's suppose that you've memorized these random mappings. How do you authenticate? Well, in our protocol, you authenticate by responding to single-digit challenges. So here's an example single-digit challenge. It's 14 images displayed on the screen as follows. And to respond to this challenge, what I'll do is I'll add the first 2 images. In this case, 9 plus 3, which is 2. Check me if I did that correctly. Now that I have 2, I'm going to look up the second image in this table. So that's these cupcakes shaped like minions. And I'm going to add this image to the remaining 2 images. And that will be my response. In this case, 7 plus 4 plus 5 is 6. All right, and so if I'm logging in and I see this challenge, I type in 6. That's my first response. And now I get a separate challenge. I solve the separate challenge in the same way and amplify security by just repeating. OK, so there's 2 things to look at, usability and security. So for usability, all we can really do is test it on ourselves and maybe look at some theoretical models of computation. So I actually have tried this. It takes me about 7.5 seconds per digit. My estimate is some of you can do this quite a bit faster. Some of you might find it takes a little bit more time. But I think 7.5 seconds per digit is a reasonably accurate estimate of the time for this particular protocol. So that's about 30 seconds for a 4-digit password, or a little over a minute for a 10-digit password. So this is a higher effort protocol to run. Memorizing the secret mapping is also higher effort. But I should stress that this is a one-time cost. Once you've memorized it, you're rehearsing this mapping every time you authenticate. So you can look at different spaced repetition models, and these models tend to predict that you're going to get all of the rehearsal necessary to remember the mapping naturally just in the course of authentication. All right, so what about security? This is where some of the technical contributions come in. So what we can prove is that any statistical algorithm for the protocol I showed you on the slides needs to see at least n to the 1.5 passwords before you can even approximately infer the secret mapping. This is nice, and in fact, it generalizes to arbitrary functions f as opposed to just the one I showed you on the slide. And you need to.
Number of images.
N is the number of images, yeah. And this 1.5 here is actually a property of the function f. It happens to be 1.5 for the function I showed you. What is a statistical algorithm? You can think of it as a giant, exponentially large tree with queries. To traverse the tree, you draw a random challenge response pair. You apply the query to that challenge response pair, and you select one of L, where L is like n to the 1.5 again, possible responses. Now, let's say you select this branch, then you draw another random challenge response pair. Use the second query function to select an edge, and you keep traversing the tree in this manner. So what we can say is that any statistical algorithm, any algorithm that you can write down in this manner, actually needs n to the 1.5 passwords before you can even approximately guess the secret mapping.
I cannot craft a challenge for you then.
Yeah, that's a good question. So you cannot craft a challenge. We're assuming this is where the semi-trusted computer assumption comes in. We're assuming that these are random challenges that you see. If the adversary can, generate his own challenges, then this bound doesn't apply anymore. We also separately show that to solve with Gaussian elimination, you need n to the 3 passwords. And also, there's an equivalence, right? You can't predict someone's passwords without knowing the secret mapping. So any adversary that wants to forge your passwords really needs to see n to the 1.5 examples. Again, assuming that the attacker is a statistical adversary or a Gaussian elimination. If I had a general statement that said any adversary or any probabilistic polynomial time adversary, then the title of this paper would have been P not equal NP, and that would be a nice paper to write, but it's unlikely. I can't prove this theorem for you in limited time. Otherwise, this theorem will become the no lunch theorem, and I don't want that. But let me just briefly hint at some of the technical tools that are used to prove the theorem. So we use the notion of discrimination norm, which was introduced by Feldman, Perkins, and Vimpala to analyze statistical algorithms. And basically, the question is, on average, how much different would the answer to a query be if we picked a random challenge and a random response as opposed to a random challenge and the true response? And if you have small discrimination norm, then you can show that any statistical algorithm needs lots of examples. So to bound the discrimination norm, we use Fourier analysis and the generalized hypercontractivity theorem. We need to generalize Feldman, Perkins, and Vimpala a little bit because we're no longer working with binary functions. We're working with functions over digits. That turns out to be the more natural base for human hardware to operate over. So there's a little bit of technical work to extend some of their theorems. So I should mention that there's a long-standing challenge to break this scheme. Each of these challenges would win you $20 if you can solve it. So there's up to $360 on the board here. I've given the challenge at Crypto and at Oakland and some other security conferences. So far, no one's broken any of the challenges, which leads me to believe that it's at least non-trivial to crack these. My guess is if you invested a lot of hardware and threw a lot of resources at it, you could probably solve some of the easier challenges, but you would really need some new algorithmic techniques to break some of these harder challenges. So just for example, this is the challenge is guess one of the user's secret 10-digit passwords, given 100 example passwords. And we're conjecturing that this is hard, and the theory and, fact that no one has actually cracked this challenge seem to suggest that it really is hard in practice as well. All right, so with that, I'll conclude and take questions.
I think there's something basic I missed. missing. The server that verifies that the user entered the correct password,
Mm-hmm.
does it have to store the mapping from images to digits?
So I guess there's two settings you could think about. One setting in which I'm only authenticating to one server, and in that case it would need to store the secret mapping and it would send me different challenges every time. Another setting, if you want to authenticate to different servers, is you just pick a fixed set of challenges for that server, and then you send those challenges to the server. So it doesn't have the random mapping. It just learns this is your challenges, and this is the response to those challenges. But that way, I could have independent passwords for Amazon, Google, et cetera.
All right, if there's no more questions, let's thank Jeremiah and the rest of the speakers. Since we're running a little bit late, we're going to postpone the start of the next session from 1:30 to 1:45. Okay, so an extra 15 minutes for lunch.